All right, we're finally ready to explain where this formula came from for the two-part loss for a variational autoencoder. So we had the prior loss and then we had the data loss. So prior loss here, data loss. Now you notice a moment ago I just talked about KL divergence, so that's the reason I called it KL div. So let me try to explain what I'm talking about here. Here was this setup that we had for variational autoencoders. And so the idea was that we had some hidden variable z that generates our x, and we want to try to learn something about the probability distributions between these variables. So z generates x, and so then I can look at, okay, a few different probabilities here. The probability of x given z is the observation likelihood. But really what I want to know is the probability of z given x. I kind of want to flip this around because I want to know how to characterize the random variable in the latent space with respect to some observation x that I've made. That's the idea. And so what I'm really interested in getting at is something called p of z given x. That's what I've called here the posterior likelihood. But what we're going to do is use an estimate called q z given x. Okay, so maybe it's not a perfect representation of p of z given x, but it's an estimate. And so let's think of the loss function that we might be able to use to compare how good qz given x is at matching the true posterior likelihood pz given x. So I want to use some kind of Kullback-Leibler divergence. That's what I just established a moment ago, that this was a good way of comparing probability distributions. And so the question is, do I want to do PQ or do I want to do QP? And so, oops, I forgot a parentheses there. That's going to bother me. So, all right, if I look at this equation here, PQ, then I have it's the weights according to the probability distribution P of P over Q. And so let me draw out maybe a hypothetical P and a hypothetical Q here. So let's suppose that our P looked like this. So maybe here's our P, and the point is maybe it's a little bit more complicated than just unimodal Gaussian, right? Maybe it's not just a Gaussian, but it's got a couple humps, a couple modes here. So this one I'm going to call P of z given x. That's the thing I want to approximate. But maybe it's easier for me to just represent a Gaussian that I'm trying to fit somehow under here. And so maybe this is my Gaussian, I'll call it Q. And maybe I'll use some different colors for this. So maybe P is going to be red and Q is going to be blue. Why not? Those are two standard color choices here. So my Q is going to be blue. And so Q, if I look at the KL divergence and how I have that set up, then what I'm going to see is if I do this one, KL divergence of PQ, then that is going to be maximized when this ratio is close to 1. So we're looking at the ratio P over Q here. So I'll just write it here so I don't have to keep going back and forth. KL, PQ looks at ratio of log P over Q. And so I have to look at, okay, when that ratio is large, I'm going to get a large penalty. So I see, for example, that ratio is very large here. And actually, like Q is really close to 0 on these tails here. So that seems like maybe not the best way to go because, you know, Q that would minimize my KL divergence there, I would have to make sure that the ratio, there was never too big of a gap between this red and this blue here, because that would be a very large ratio that would really pull up my KL divergence, right? If P over Q is large, that's going to be huge in the sum here. So looking back at that. And so what that would do is that would force, so I'm trying to drag this over here. That would force my distribution to go out like this to avoid that, right? So I want to make sure that the tails were never under that distribution. So I'd be forced to make this very wide. And that may not be the best way to go here. In practice, I would actually prefer for this blue curve to be, even if I'm not capturing both modes, it would be better if the blue curve were under the red curve. So it turns out I actually want to switch the ratio around. So if I do KLQP instead, then I'll be looking at the ratio of the log of Q over P. And in this case, this is more the answer I'm going to get. So this is what I'm really trying to minimize. And so now I don't have so much of a problem. When Q is small and P is large, I don't really have much of a penalty at all. The only places I really have to worry are here. So I just need to make sure that you know, Q is should kind of stay under P. That's the idea. So it's a little bit strange to get used to, but the point is, you know, I'd prefer to capture one of these modes really well than to do a mediocre job capturing the whole thing. That's the idea. So really here, we're going to roll with the KL divergence of Q Z given X, to be more specific there, P Z given X. So I'm going to stay here, you know, given that Q Z given X is learnable. So maybe I'm modeling Q Z given X as a Gaussian, so I would learn its mean and standard deviation. All right, so if I just plug this in for the discrete formula for Kullback-Leibler of Q Z given X, P Z given X, then I end up with this equation here. And if I abuse notation a little bit, I can write this as it's really an expectation over using the distribution Q Z given X of this quantity, natural log of Q Z given X over P Z given X. And what's interesting is I don't always have access to this P Z given X. That's what's called the posterior likelihood. And sometimes I don't have it explicitly. Sometimes it's just really nasty to write down or to compute, and it's not worth computing it. And so what I can do instead is use Bayes' rule and plug in this expression, which is in terms of the observation likelihood, latent prior, and observation probability, in the place of PZ given X. So if I do that, it's just some reciprocal stuff. So if I plug in for PZ given X, Bayes' rule, then that, you know, it's Px given Z times Pz over Px, and I bring that Px up to the numerator, and then I have this here. And so what I'll do is I'm going to keep working with this equation here, but I'm going to split some stuff up according to log rules. So what I'll do is I'll take out this Px by itself here. So, you know, I've said this before, but I've used this before in this video series, but I'll just remind us again that log of A plus B, or sorry, log of AB is equal to log A plus log B. And then we also have that the log of A over B is log of A minus log of B. All right, so applying these rules here, what I'm going to do, I'll take this, so this Px in the numerator, I'll take that out by itself into a log. I will keep the Qz given X over Pz in there, but I will take the Px given Z out of there, of the denominator. So that'll come out as a negative log. And let me see if I got that right. Okay, so yeah, this is, oops, I should have said natural log of P of X plus. So again, just applying those log rules there, and this is the expression that I end up with. So out of these three terms here, this term is the only one that doesn't depend on Q at all. So when I integrate this or sum this over all possible values of Q, that's going to be like a weighted sum that sums to 1. And so actually you can just pull this out of the expectation here. And so this is something that will be off to the side by itself. And actually I'll remember the before and after here. So I'll say, you know, we can pull the log probability out by itself because it doesn't depend on Q of Z given X. So that's a move that we'll do here. and we end up with this. All right, so if I move things on either side of the equals sign, I can rewrite the above equation like this. And now I can start to build towards some intuition here by noticing that I kind of have a new goal in mind. I want to maximize the left-hand side here. And really I want to maximize P of x. And so I want to maximize the probability of x, the prior probability of x. So that's like saying the prior probability of x is like, how close are you to being part of the data distribution? In other words, if I'm trying to fit this thing to cats, I want this variational autoencoder to represent cats. P of x would say, how likely is this particular image x a cat? And I want that to be as big as possible. If I subtract the Kullback-Leibler that I started with, originally I said I wanted to minimize this difference between these two different distributions. Maximizing the left-hand side is like saying I want to maximize this and I want to minimize this. Because this is non-negative, it's only going to detract from this probability. And so I could say, okay, I want to maximize the left-hand side. It's really equivalent to minimizing this Kullback-Leibler divergence, because that's actually something I have control over with this Q of z given x. So that's another way to look at what's going on. Now this is called the evidence-based lower bound. So the name for left-hand side here is the evidence-based lower bound, which we call ELBO so that we can be fun with this. So of course in this equation here, if I'm maximizing the left-hand side, it's equivalent to maximizing the right-hand side. So this is equivalent to maximizing the right-hand side, which is equivalent to minimizing the negative of the right-hand side. So let me pull that out and show you what I mean. So if I take this out and I take the negative of it, I'm saying, maximizing the evidence-based lower bound, getting as close as I can to the probability of x, is like minimizing over this choice of a posterior likelihood approximation. So it's like minimizing over that the expectation of this natural log minus the natural log of p x given z. So let's just look at that and see if that looks right. So I just negated this and I negated this and then I have that, and the max turned into a min. So this is like what I'm trying to do now. So it's interesting, if we look at this term here, this is actually a KL divergence of QZ given X PZ. And so that's how I can treat this expectation, and then I'll just subtract the expectation of that. So if I rewrite that, I can rewrite this actually as this. So now we're getting really close to a final expression for a loss function that we want to try to minimize. Right? So what I'm trying to do here is maximize the evidence-based lower bound. And that boils down to an equivalent minimization of this Kullback-Leibler divergence here minus this expectation. Now if I go back to my code, I can actually match this equation up exactly to what I have here. So that's what this KL div term is here. It's the KL divergence of the Gaussian that we're trying to fit. So this mu and the sigma is QZ given x here. So we're given an x and we compute the mean and the standard deviation of the distribution of our posterior likelihood. And then PZ, that is the prior, which we assume to be a unit Gaussian. Mean 0, standard deviation 1. And then we have this fit term here, which also comes out of a Gaussian. But let me focus on the KL divergence first. So I'm actually not going to derive this whole equation. I'll just jump to the Wikipedia page for KL divergence here and show you that they've already done that. If they're Gaussians, just like we have here, two Gaussians. So we've got the Gaussian that we're learning and the prior, which is the unit Gaussian. Actually tells us if the prior is the unit Gaussian. So there it is. Just to show you again, that's where it showed up in the equation. So our prior is the unit Gaussian. So if that's what we have on the right of the Kullback-Leibler here, And then we have our own Gaussian here on the left where, this is what we're learning, QZ given X. We've got all our means and all our sigma squareds here. Then this is the formula for the KL divergence. And so I literally just plug that in here. So it's great because everything is a Gaussian. Whoops, let me get back to you. Yeah, it's great because everything is a Gaussian. So I was able to just plug that in. So the only other thing I need to explain here is why do I have this particular fit for my loss? Okay, so if we go back to our equation, somehow that's this second term here. And it's related to Px given z. So Px given z, that is the observation likelihood here in Bayes' formula. So given a latent vector, that's how likely it is that I would have had this input x to my autoencoder. Now what's actually happening is it's reconstructing an estimate. And so I can characterize that probability by saying, well, I sample one of my latent codes, and I use that latent code to reconstruct or send through the decoder an estimate. That estimate should be close to this here. And so what I can do is make the input here be the mean. Each dimension here will be distributed as an independent Gaussian with a mean equal to what the pixel actually is in the input image. And then I'll compare that. I'll use that Gaussian distribution to compute a probability of this output. And so putting it all together, it's like I'm going to compute the probability of this given a particular latent vector sample by looking at what that latent vector sample would construct and then treating that as a Gaussian. So this is a bit of a conceptual leap, but let me just show you the math. Because if I take this equation for a Gaussian probability, so I'll just show you this in one dimension here. If I went back to my equation here and I took the negative of the log of that. So let's just look at that for a second because I think that'll help explain why we're doing the sum of squares here. So if I take the negative of the log of all this stuff here, of all this mess, then what that'll do is that will bring down this stuff in the numerator. So we're using natural log here. So natural log of v is 1, and I'll just bring this all down. So that is equal to a constant. So it's a little messy, this 1 over 2 pi, and that's kind of beside the point here. So it'll bring down a constant minus negative this stuff that was in the exponent before. So minus the negative is a plus. And so when I take the negative natural log of that, I get some constant plus x minus mu over 2 sigma squared. So here, mu is what the pixel was in the input, and then x is what the pixel was in the output. And so now this is looking a heck of a lot like the equation that I had back in my code. So it was x minus x out quantity squared, summed up over everything. And so yeah, so that's just going to sum that up over all the Gaussian dimensions. So the only difference here is we have a constant up front, which really comes out in the wash. And then we have this sigma term here. Now remember, when I did this, I set it up so that I could come up with this weighting between, how much did the loss prior, how important was that compared to the fit. And so really that's where the sigma squared comes from in here. That's somehow related to the lambda. The more uncertain that I am about my fit, the more uncertain that I am about my observations given the latent vector, the higher my lambda would be, the higher that I would say, well, I want to then put all my eggs into the prior. I'm so noisy here that I kind of want to rely on the prior more. But yeah, just for me, it was always an aha moment when I looked. I said, well, if you take the negative log of a Gaussian probability, it's the same as the sum of squares. That's really what I'm trying to get you to see here. So if you got nothing else out of that last bit there, hopefully you got that. And then that explains why the second term looks like this. So first term is Kullback-Leibler, second term is this. And that's our evidence-based lower bound. And yeah, we're trying to maximize the evidence-based lower bound, and then I ended up taking a negative here, and I'm minimizing this. Okay, one last bit of intuition that I want to point out about this equation is what the direction of this Kullback-Leibler here says about how we're making our posterior likelihood fit underneath the prior. So going back here, it's really the same argument that I made when I started off, although I think it's a little bit more intuitive to see this one. So I had to wave my hands a little bit on the first one when I was talking about why it would be a good idea to fit an approximation under a single mode. To me, that's a little bit less clear than the fact that when we do the evidence, somehow this is what we do to get the evidence-based lower bound. Once we get it in that form, it's actually a lot clearer. We see if we have a prior, so our prior was this Gaussian that was a unit norm, if you remember. So here is our prior. I'll draw it in red. And that is something that we're going to fit our posterior likelihood underneath. So the posterior likelihood could be pretty tightly coupled around, or it could be pretty tightly concentrated around a particular z. And that's fine. It just has to be underneath this. And so that's when we go back to some of the examples that we had when I was looking at the digits, for example. That's why I kind of stayed underneath that blob. I didn't go too far away from the blob, especially when I really highly preferred to match that prior, when I really highly penalized a KL divergence that wasn't 0. So anyway, I just wanted to show you why this is intuitive here. So we're forcing our posterior likelihood to be under the prior. And that's why we never went outside of the prior. All right, well that's it for now. We'll take a little pause and then I'll show you some other generative techniques. But I hope this was illuminating, and I really hope that this helps some people who were trying to understand the intuition behind this math. I tried to put a lot of stuff in one place that I never really saw all together in one place.